In the previous lecture, we had seen the listing of the a priori algorithm for carrying out association rule mining, but I'll hurriedly go through it once again because this is a very important algorithm. And let me also tell you that this is not the only algorithm for association rule mining. Many more have come up, but this is just to give you an idea. So once again, we are starting with the set. Just hold on, let me take the pen. Yes. So we have to start with the set of all single keywords. When I say keywords, it again means I'm saying about the frequent terms or the terms which qualify the minimum threshold, support threshold. So I have to count all such single frequent keywords or frequent terms. Then I set the index 2 because S1 has already been found out. I'll be building on that. So while sk minus 1 is not equal to null, since k has been incremented to 2, that's why sk minus 1 would mean that S1 in the first loop. So if S1 itself is null, that is there's no single keyword which is frequent. So obviously the algorithm will terminate there itself because there's no way the anti-monotone property tells us more combinations which are above the minimum support threshold. So we'll check here itself. While sk minus 1 is not equal to null, do begin. Potentially frequent higher order set. So C2 in the first loop. C2 that will work on the frequent S1, the set of all single keywords. So join operation will happen. And then again, the same CK will undergo prune using SK minus 1, and I'll still have the potentially frequent K frequent item set. So in both these, join and prune are still giving me the potentially frequent item sets, K item sets. So now Sk is equal to null for each element that belongs to this Ck which has been found out after joining and pruning. I'll go to the transactional database and I'll actually do the count on the transaction database T for every element V in Ck. So if this goes above minimum support, then I'll keep on adding that element to my Sk. Finally, when all the elements in Ck have been exhausted, this loop will come to an end, K will be incremented, and I'll go back here. I'll go back here and check whether the Sk that I've found out is null or not. C3, join S2, C3, C3 and S2, Sk is equal to null, which will be S3 is equal to null. I'll go on doing it while I'll come across a case where my actually frequent item set becomes null. When it becomes null, I'll abort, I'll come out, and then I'll do the printing. And while printing, I'll start with 2. Why? Because S1 is not of much use in the final tally. It was important to begin with S1, but since a single keyword cannot form association, you cannot have a single word or a single term association. So I'll just exclude it. Association requires at least 2 of the key terms. So that is why I is equal to 2 to K minus 2. Why K minus 2? Because I had incremented K here, and even before that it was a null set. So there's no point in including the null sets, right? And SI. So that will be the final printing. So I'll urge you once again to write the algorithm, to write the code for running the a priori algorithm. This should not take too long. If you have done the previous exercise in which I told you to list all the subsets of a given set, then it would not be a problem for writing the a priori coding. Let me elaborate with the help of an example. I'm talking about the same transaction database that I had taken in the beginning. My first step is to find all single keywords. All single keywords I'll have to find out. So we'll have to find out the single keyword frequent item sets anyway. So one item set bread occurs in 4 transactions. 4 means 4 transactions. Coke occurs in only 2 transactions, and support, my minimum support threshold was 3. So 2 comes out to be less than 3. Milk appears as a single item in 4 transactions, beer in 3, diaper in 4, and eggs also appears in just 1 transaction. So both Coke and eggs both are having a lesser threshold, right? They are having a frequency in transaction database which is lesser than the threshold. So I can exclude them here itself. I can exclude them here itself. The combination that I'm going to make will be bread, milk, bread, beer, bread, diaper, and so on. I'll not make bread Coke and bread X, for instance. Similarly, I won't make milk Coke. I'll just have milk beer, milk diaper, and I won't have milk X either. So basically, Coke and X will not take part in any further combination, which means a lot of saving. We will shortly see it means a lot of saving, right? So many more transactions, so many more combinations, that all has been avoided, right? So these two are simply cleared here itself. So now I'll have the combinations: bread, milk, bread, beer, bread, diaper, milk, milk, diaper, beer, diaper. After making these combinations, it is still a potentially frequent item sets. I'll actually go to the transaction database and I'll see now how many times these combinations are appearing. So bread milk is appearing 3 times, bread beer appearing 2 times, which is less than the support threshold, bread diaper 3 times, milk beer 2 times, again less than. So basically these 2 combinations will again be cleared off, right? So now my combinations for 3 item set is bread, milk, diaper, beer, and this again will go off, right? Because this is less than. So if we would have to consider all possible subsets, then we would have to work with 6C1 because there was total 6 items. So single frequent item set would be 6C1 plus 6C2 plus 6C3, which will come out to be 41 combinations in all. 41 combinations mean all these 41 combinations would have to be taken to the actual transaction database and done the frequency counting. However, with support based pruning using the anti-monotone property, only 6 plus 6 plus 2. See, only 6, 1, 2, 3, 4. Out of this, we had to do for 6. Then we had to do for 1, 2, 3, 4, right? And we had to do for 2 only, right? So, sorry, hold on. We just had to do very few combinations for actual frequency counting. I think even this one will be 4 only. This one will be 4 only. Why I'm saying this? Because see, I had to do the counting for 6 of them, right? Over here, no, I had to anyway, because eating that I'll get to know that there is these 2 have to be pruned off and then 2. So this was correct. 6 plus 2 is equal to 14 combinations. This one was wrong. So a total of 14 combinations are to be tackled for the actual frequency counting. So 41 compared with 14 only. See, so much saving has been done using the a priori algorithm. Now there could be so many combinations for carrying this out. This was the bottom-up approach. We took S1 first and made C2 and then S2 and then C3 and S3. We are going bottom-up. Some people were thinking to go top-down, take the largest combination first. If it isn't satisfying the minimum support threshold, go for the next one, next one, next one. So a lot of studies have already been done on this. But this is one of the algorithms which has become very successful. So I would urge you to develop the code for this a priori algorithm. Now this is despite the fact that I have just 14 combinations. This was a small example anyway. Think about a case where you have 1,000 items in a big store. And even million items may not be too much for a big departmental store. If you go for online stores, that may run into several millions. So in such a situation, even after doing the joining and pruning, this number would be too large. So it becomes computationally intensive. So people have devised some parallel association rule mining algorithms. Need for parallel algorithms comes from too large the transaction database. The database itself may be large. We have just taken the example of 5 transactions in the database. This may be several millions transactions, and or too large the possible number of frequent item sets. Again, if these two get combined, the computational intensity becomes that much more. Correspondingly, the candidates need to be counted in parallel and or they need to be generated in parallel, right? So this will amount to this and this amounts to this. So if you want to bring in true parallelism, you will have to do both these things in parallel and generate them in parallel. So I think this is pretty straightforward. One of the parallel algorithms is count distribution algorithm. Each processor computes how many times all the candidates appear in the locally stored transactions. The global counts of the candidates are then computed by summing these individual counts using a global reduction operation. So what we have distributed is, this is the count distribution algorithm. So for example, transaction 1, 2. Its count is 2 here, 7 here. So we have basically divided the entire transaction database in P processes. So n by P, n by P, n by P, so on. So over here, 1 by 2 is counted. Frequency is 2. Over here, it's 7. It's 0. It's 3. So I'll do the summing. 2 plus 7 is 9. Plus 3 is 12. So I'll say 1, 2 is appearing 12 times in the entire transaction database. So likewise, I can do 1, 3, 5 times, 3 times, 2 times. But I'll have the global addition, global reduction algorithm for addition, and that will give me the total count. So in count distribution algorithm, I am dividing the transaction database into P processes. Pros and cons of count distribution algorithm. This algorithm is shown to scale linearly with the number of transactions. Very good, because we are dividing the number of transactions in P processes. So it has to scale linearly. However, this algorithm works well only when the number of candidates is small enough to fit in the main memory. Suppose this list itself is too large. There will be 3, then there will be 4, and so on. Now, if this list itself is so large that it cannot fit in the RAM, and it has to be brought in from secondary memory when it is being counted and then shifted back to the secondary memory after the count is done, that will amount to a lot of time wastage in doing the movements, right? So that is where count distribution algorithm fails. When the number of candidates is large enough to fit in the main memory, it will fail, and it will succeed only when the number of candidates is small enough to fit in the main memory. Note that the number of candidates increases if either the number of distinct items in the database increases or if the minimum support level of the association rule decreases, right? So these two conditions are going to give me more and more candidates, right? When the transaction database becomes too big or the support is decreased. When the support is decreased, the joining and pruning will be joining and pruning lesser number of candidates. So more candidates, their frequency will have to be counted. Thus, the CD algorithm is effective for a small number of distinct items and a high minimum support level. More the number of items, more will be the combination, so the list will become too large. And if the support is also low, that list will stay. Most of the items will stay to be counted. So it works effectively for a smaller number of distinct items and a high minimum support level. Small number of distinct items and a high minimum support level. Only then it will work. Let us move on to the next one, data distribution algorithm. Memory problem of the CD algorithm is addressed by partitioning the candidate item sets among the processors. Partitioning is done in a round-robin fashion. Each processor computes the counts of its locally stored subsets of the candidate item sets for all the transactions. Each processor needs to scan the portions of the transactions assigned to other processors as well as its locally stored portion of the transaction. Again, the database is divided anyway, n by p, n by p, n by p. What I am doing is that I am distributing the candidates also 1 by 2 in a round robin fashion. 1, 2 here, 1, 3 here, 1, 4 here, 2, 3 here, 2, 5, 3, 4, so on. So it will have to count not only over here, but it will have to count in the transaction database here too, in the transaction database here too, in the transaction database here too, like that, so that the overall count is found out. So this will be data distribution algorithms. Not only the transaction database is distributed, but also the job assigned for a candidate is also distributed. Candidates are also distributed. This algorithm exploits the total available memory better than count distribution. As the number of processors increases, the number of candidates that can be handled also increases. However, the performance of this algorithm is significantly worse than the CD algorithm. Why? Because for counting 1, 2, it won't have to go just here. It will have to go here also, which is remote, to here, which is remote, here, which is remote, right? So that is why they're saying the runtime of this algorithm is 10 to 20 times more than that of the CD algorithm on 16 processors. The problem lies with the communication patterns of the algorithm and the redundant work that is performed in processing all the transactions, right? So it will have to go to the remote sites. So this was about the data distribution algorithm, which apparently looked that it is going to help us, because it is not only distributing the transaction database, but also distributing the candidates. But in the final tally, it didn't help. Then we went for intelligent data distribution algorithm. Compared to data distribution, where all the processors send data to all others, IDD performs point-to-point communication between neighbors, eliminating the communication contention in data distribution. To eliminate the redundant work in data distribution due to the partitioning of the candidate item sets, IDD partitions the database among processors in such a way that each processor gets item sets that begin only with a subset of all possible items. Let me show it here. So I have a bitmap. Instead of just distributing n by p, n by p, n by p, what I'm doing intelligent data distribution. N by p, this n by p will have all the transactions which contains 1 and 7. This will have all the transactions. There may be duplication also, but it will have all the transactions which contains 2 and 5. It will have all which contain 4. It will have all which contain 3, 6. So that for counting any candidate containing 1 and 7, it doesn't have to mainly go to remote sites. It may have to go, for example, 1, 2 is all here, so it'll count here itself. 1, 3 is entirely here, it'll count here. 7, 8 is entirely here, so it'll count here. It may not be required to go to these remote sites, except maybe some sparing cases, but that will be very low, right? So all what has to do with 2 and 5 will be available here mainly. All what has to do with 4 will be available, even if it means duplication of transactions, because there could be a transaction which contains 1 and 5. Okay, so 1 and 5, that will be here as well as here, right? So it will be at both the places. So this is about intelligent data distribution algorithm. So having said or having told the problems with the parallel algorithms, they still perform better than a sequential a priori algorithm. Pros and cons of IDD. For each transaction in the database, IDD partitions the amount of work to be performed among processors, thus eliminating most of the redundant work of data distribution. However, partitioning this way may cause improper load balancing, particularly with a smaller number of candidates. ऐसा जरूरी नहीं है कि 1, 7 और 2, 5 का जो बिट मैप होगा उसमें ये बिल्कुल n by p हो जाएगा. हो सकता है ये बहुत ज्यादा हो n by p से, ये बहुत कम हो n by p से. So जो load distribution हुआ वो uneven हो गया, because it's not like paging, it's like more like segmentation, है ना? मतलब logical distribution है, it is not a fixed size distribution. इससे पहले हमने देखा था वो दोनों में CD और DD दोनों में that was a fixed size partition. तो ये improper load balancing की problem आ सकती है, particularly with smaller number of candidates. Candidate small होंगे तो ज़्यादा load balancing के chances बढ़ जाएंगे, क्योंकि duplication जो है वो heavily unbalanced हो जाएगा. तो ये थोड़ा सा एक आइडिया था कि इसको पैरेलल कैसे कर सकते हैं. ठीक है, अच्छा. load balance in IDD by combining the CD and the IDD algorithms. For a P-processor system, the candidate set is partitioned into G groups to just fit in memory. This ensures good load balance even with a smaller candidate set. So this is how research progresses. You do something, there are problems, you try to solve them. There may be more problems of another nature, you try to solve them as well, in addition to the initial problem. Effectiveness of an algorithm. So we logically arrange those processors in a G cross P by G mesh, perform IDD along the column processors, the data movement among processors is minimized, perform CD along the row processors, the global reduction operation needs to be performed in a smaller number of processors. So I'll show you the chart here. All-to-all broadcast of candidates, IDD along columns, G groups of processors, and P by G processors per group. And CD count distribution along the rows, right? So that is how you have the hybrid distribution algorithm. Relative performance of the parallel association rule mining algorithms. Algorithm CD, computational complexity is low, communication complexity is low, load balance is good, scalability is very poor. So this table will give you an idea how they are relatively performing. DD, computational complexity is high because now you have to go to the remote sites also. Communication complexity is higher still. Load balance is poor, scalability is good. IDD, computational complexity is low, communication complexity is high, load balance is good. Distribution, computational complexity is low, communication complexity is low, load balancing is good, and scalability is good also. So we see that in the final tally, our hybrid distribution algorithms perform better as compared to count distribution DD and IDD. So this was our relative comparison of the 4 parallel ARM algorithms or association rule mining algorithms. So some revolutionary work in this area of parallel mining of association rules needs to be done. Revolutionary in the sense that the inter-processor communication must be drastically reduced. This may even have to be done at the cost of losing a few association rules here and there. So that is a very interesting line, which are also called the approximate algorithms, in which we don't go for the bull's eye. We say that let me finish somewhere close to the bull's eye, but let me do it quick. There are many approaches this way, like genetic algorithm. It starts with a very vague solution, then it keeps on slowly building up to the actual solution and gets very close to the actual solution. So if you lose an association rule here and there, but you are able to do it quickly, that may make more sense. For example, transactions happen today. Now you're going for an absolute algorithm. Each and every association rule you want to have. That may take a week or so. By that time, may have done his job in an approximate way, may have missed a rule or two, but may have given the solution in just a day. So they may improve upon their store in just a day where you have taken a week. Okay. So engineering is all about optimization, right? The best possible result in a reasonably good amount of time. That may be the approach that we may have to follow. So that may be one line of action where you are getting a reasonably good result. But also the errors arising out of it. Okay, so we basically have to reduce both. Computational complexity must be reduced and errors should also be minimized, if not completely done away with. So this was a brief introduction about the association rule mining, which is one of the data mining tasks. Next, we would move on to web mining. How can we apply this association rule mining algorithm along with other algorithms for carrying out web mining? So let me take up the case of association rule mining itself. What you can do, you can use this association rule mining on the web for what is called web caching. Web caching is one area where you can, what do you mean by web caching? While you are looking for one home page, you were just reading this web page, your system should be intelligent enough to fetch the next 1 or 2 pages that you are likely to visit. How can you do that? Make use of association rule mining. How many people who visited this page also visited this page? So if you have that support as high, or the confidence as high, confidence basically depicts the strength of connection between these 2 pages. So if it is high, why don't you prefetch? Why don't you prefetch 1 or 2 or 3 pages? So that as soon as you clicked a particular link, that page should immediately open from your local disk rather than going to the actual site and retrieving it. You got the idea? So you can use it for web caching or prefetching of web pages. But you should know the association between them. How closely are the 2 pages associated with each other? Right? There may be a set of 5 pages that are closely associated with this one. You prefetch all 5 of them when this is being read, right? So that is how you can do prefetching using association rule mining. Likewise, if you use classification and clustering, you may have seen that when you launch a web search query, you end up getting 1,000 results or 10,000 results. Now it becomes very difficult to go through all those 10,000 results to get the relevant item or relevant page. So what you can do is, why don't you cluster your results before you present it before the user? Let me give you a very specific example. There is a word cricket, right? All of us are familiar with this word, but there is semantic ambiguity in this cricket word. Cricket is a sport. Cricket is also an insect. Now you launch the query using cricket. So all your results contain sports as well as the insect information. What you can do better is you prepare 2 clusters. One is a zoology cluster, the other is sports cluster. And then you present them before the user, tell them that, look, I have 2 clusters for you. One, the other pertains to the insect or zoology. A zoology may go for this cluster, whereas a zoologist may go for this cluster, whereas a sportsman may go for this cluster. A very basic example I've given you. So likewise, you can have more than 2 clusters also. So all the 1,000 results will now be reduced to 500 each, approximately 500 each. If you form more clusters, right, it may even reduce further. For example, within cricket, you can say, this is the cricket batsman cluster, this is the cricket bowler cluster, this is the cricket all-rounder cluster. So if somebody wants to look at this information, he can go for batsmen, then for bowlers, then for all-rounder, fielder, and so on. So you can have several clusters. So the search result may not be a monolithic search result. I hope you know what is monolithic. Monolithic means everything on the same surface. You try to form clusters out of it. It helps. You try to form clusters, it helps. One can pick up a particular cluster. And if in the worst case he has to go through all those pages are there anyway. You can take them cluster by cluster rather than taking them in a haphazard way from one to the next and so on. So this is just a glimpse of how web mining can be done. I'll cover it in my subsequent lectures, but as of now, just understand that web mining may broadly be classified into either web content mining or web usage mining. Web content mining or web usage mining. So we will take them one by one. Web content mining as well as web usage mining. So I'll stop here for today. Try to go through it. Lot of new algorithms I've taken, the parallel ones. In fact, the algorithm was the old one a priori, but I have taken the parallel versions of them and some glimpse into their pros and cons and some concluding remarks on data mining. From next lecture, we are going to get into web mining, which is our main focus. Thank you.